Okay, so today we will continue our discussion of protecting groups in peptide synthesis. Then we'll talk about another way of synthesizing peptides involving solid phase, where we anchor our peptide to a polymer and add it one amino acid at a time to the polymer. And then we'll conclude with a discussion of protein structure. So where we left off on Monday was with this general description of how we can synthesize a dipeptide. We need to use protecting groups to block the functional groups that we don't want to react. Then we perform our amide bond forming reaction, and then we remove one or both of the protecting groups. And we'll talk about that in a moment. We taught you that carbamates are the functional groups that are used to protect amines. And we taught you two common carbamates, the Boc group and the FMOC group. The Boc group is cleaved using acid, and we went over the mechanism of that. The FMOC group is cleaved using base. We get the aromatic conjugate base. There is a third protecting group, third carbamate protecting group that is not in the textbook, but is important to know, and we'll explain why that is in a few moments. And that is the carbobenzyloxy group, otherwise known as the CBZ group. So this has a benzene ring in it, and it is installed using a chloroformate reagent. We use the FMOC chloroformate to install the FMOC group. So this reagent is very similar to the one used for FMOC. It's just that we have this benzyl group here as opposed to the that fancy aromatic system of the FMOC. And we use the sodium carbonate to deprotonate our ammonium ion. So it reacts with the chloroformate in the same way that an amine would react with an acid chloride. And then we get our carbamate at the end after the proton transfers and eliminations. Okay. And we typically use CBZ as an abbreviation for this group. So feel free to use that abbreviation. Use any of these abbreviations, Boc, FMOC, CBZ, if you are writing out a synthesis of a peptide. So the reason one would use an FMOC group, or sorry, a CBZ group to protect the amine of an amino acid is that it is cleaved under unique conditions. It can be cleaved using HBr. That's not that unique because the Boc group is cleaved using either HCl, TFA, or HBr. But what is unique is that it can be cleaved using hydrogen and palladium carbon. Okay, we'll talk briefly about this HBr cleavage. We won't draw a mechanism because it's going to be the same mechanism that we used to cleave the Boc group with acid. We protonate the carbonyl. In the case of the Boc group, we lost a tert-butyl cation, a tertiary carbocation. In the case of the CBZ group, we're losing a benzyl carbocation, a resonance-stabilized cation. And then that benzyl cation just reacts with the bromide, and then we would get a carbamic acid, which fragments and loses CO2, just like we talked about with the Boc group on Monday. But the unique aspect is the cleavage with hydrogen and palladium carbon. So we've learned that hydrogen and palladium carbon is very good for reducing carbon-carbon double bonds and carbon-carbon triple bonds. We don't see any carbon-carbon double or triple bonds in this molecule. But what you haven't learned yet, what we're teaching you now, is that benzylic carbon-oxygen sigma bonds are able to be cleaved using hydrogen with a palladium catalyst. So when we treat a benzyloxy carbamate or carbobenzyloxy group with hydrogen and palladium carbon, this carbon-hydrogen bond, sigma bond, carbon-oxygen sigma bond, is cleaved, and we end up bonding hydrogens to each of the atoms that were involved in that sigma bond that is cleaving. So when we bond a hydrogen to this carbon, we end up with toluene. Okay, toluene is often used as a solvent. It's a liquid. It's easy to distill off from your reaction mixture, so it's very easy to separate from your desired product. And then when we put a hydrogen on this oxygen, we end up with something known as a carbamic acid. And we saw that as an intermediate in the cleavage of the Bock group. What happens to the carbamic acid? It doesn't last very long, if you remember that mechanism. What happens to it? Yes, Sydney. Yes, it loses CO2 very readily. So we're not even going to draw it here. We're just going to draw CO2 will form. And then you will get your amino acid. Okay. And in most cases, it's not really the amino acid. Usually you have already made a peptide bond by the time you cleave this off. So usually it's a peptide chain that has an amine, a free amine on the end. So very simple, easy way to deprotect hydrogen and palladium carbon. Any questions? Okay, so that's 3 carbamate protecting groups we've learned: Bock, FMOC, and CBZ. And the important thing is to know how to install those groups, to know the structures of those groups, and also to know the conditions for cleavage. And in the case of Bock and FMOC, we taught you the mechanisms, right? This mechanism we just described. We wouldn't draw out a curved arrow mechanism for that. So now we're ready to talk about protecting the carboxylic acid groups of peptides. And for that, we use a functional group we've already encountered, and that is an ester. We just make esters of those carboxylic acids. So the book teaches you 2 of them, and just like we did with the carbamates, we will add a third, but first we'll teach you the 2 esters that the book uses. We can make a methyl ester, and to do so, we simply use a reaction we previously used to make esters. That is the Fischer esterification. Okay, so if we use acid and methanol, we'll first protonate our carboxylate to make the carboxylic acid, and then we can perform the Fischer esterification mechanism to install a methyl ester. And of course, because we're using acidic reaction conditions, your unprotected amine would be present as the ammonium ion. And then the other ester that the book teaches you is the benzyl ester. So we can use benzyl alcohol. Benzyl alcohol is not phenol. It's important to know the difference. Benzyl alcohol has an sp3 carbon between the oxygen and the benzene ring, whereas phenol has the oxygen directly attached to the benzene ring. Okay, so this is benzyl alcohol and not phenol. You use that with acid. We have the same mechanism, the Fischer esterification mechanism, and we end up with a benzyl ester. Okay. And because we like abbreviations, we use the abbreviation BN for benzyl. Okay. So we use that abbreviation frequently instead of drawing out the structure of the benzyl ester. Okay. So we install the methyl and benzyl esters using reactions we've learned previously. How would we cleave them? How would we remove those groups? What reactions do we know that hydrolyze esters? Think back to chapter 22. How do we cleave esters? Yes? Okay, so we can use the reverse of the Fischer esterification. We could use strong acid. We typically don't use that because that can also sometimes cleave the amides that we've just worked so hard to form. Yeah, strong base also works. The saponification, that actually works better because if you're cleaving amides with base, it usually takes longer than cleaving esters with base, and you usually have to use heat. The saponification reaction is a nice irreversible process. It's usually fairly quick. And so that is the way that you're going to cleave methyl and benzyl esters, just using aqueous base, okay? And that's just going to be a saponification reaction, a mechanism that we have already learned. The benzyl ester has a second set of conditions that you could use, right? If you were installing and cleaving the methyl and benzyl esters under the same reaction conditions, you'd probably never make the benzyl ester because it's bigger. You would just stick with the methyl ester. But the benzyl ester can be cleaved using hydrogen and palladium carbon, just like the benzyl oxy or the carbobenzyl oxy group can. Okay, we have a benzylic carbon-oxygen bond. As we learned, whenever we have a benzylic carbon-oxygen bond, that can be cleaved using hydrogen. Okay, we get our toluene liquid byproduct, very easy to remove. In this case, we don't do a decarboxylation like we did with the carbamate. In this case, we just directly obtain the carboxylic acid product from that hydrogenation reaction. Okay, so two choices with the benzyl ester, and there's actually three choices. The benzyl ester can also be cleaved using HBr. Okay, and that mechanism is going to be very similar or comparable to the cleavage of the CBZ group with HBr. We would protonate the carbonyl, and then we would simply lose the resonance stabilized benzyl carbocation, and then the bromide would attack that benzyl carbocation to give us benzyl bromide as a byproduct, and we would have our carboxylic acid. Okay, so we're not going to draw that mechanism, but based on the description I've given you, you ought to be able to draw that mechanism on your own. So there's actually three ways we can remove a benzyl ester: aqueous base, hydrogen palladium carbon, or HBr. Questions? Okay, so there is a third protecting group, a third ester that is used that the book does not teach you, and that is the tert-butyl ester. And the tert-butyl ester is synthesized in a special way. You can't make the tert-butyl ester using a Fischer esterification because tert-butyl alcohol is very, very bulky. And so the tert-butyl alcohol does not attack the carboxylic acid carbonyl very readily. So we have a different way of synthesizing a tert-butyl ester that will show you. We react our carboxylic acid with an alkene. This is 2-methylpropene. And we use sulfuric acid in the reaction. So the sulfuric acid is going to protonate the alkene. If it protonates the alkene, it's going to give us a tert-butyl cation. That tert-butyl cation is attacked by the oxygen, and that's how we generate our tert-butyl ester. Okay. Okay. All right, so why would we want to make a tert-butyl ester as a protecting group for carboxylic acids? Well, the reason we would want to do this is that we can remove the tert-butyl ester under reaction conditions that are different from removing the benzyl ester or the methyl ester. And as you'll see, they're the same conditions that are used to cleave the Bock group. Okay, so we can use HCl. We can use trifluoroacetic acid. or we can use HBr. So it's easier to remove a tert-butyl ester using acid than it is to remove a benzyl ester. The benzyl ester has to be HBr, but we could use HCl or trifluoroacetic acid, which are not as strong acids, to cleave the tert-butyl ester. So the mechanism of that process, we'll show that to you here. So if we react this compound with HCl, as we've done repeatedly, we'll protonate the carbonyl group. Giving us the conjugate acid of our ester. Okay, we generated chloride, the conjugate base of HCl. So this species can undergo cleavage of the carbon-oxygen sigma bond here. Okay, and that's going to give us our carboxylic acid. Forgot to put the R group on. Okay, so here's our carboxylic acid. We generated a tert-butyl carbocation in the process. Obviously, that's not going to be stable. That's not going to survive as a tert-butyl carbocation. Much like we did in the Bock deprotection, we'll use our conjugate base of our acid, chloride in this case, as a base for deprotonating that tert-butyl carbocation, generating the alkene, 2-methylpropene, and regenerating our acid. Okay. Any questions about cleavage of the tert-butyl ester protecting group? Okay, so now that we've learned the identities of specific protecting groups, we can replace this figure on the screen that just shows the protecting groups as these tan boxes. We can replace those with actual protecting groups. Okay? And there's more than one way to do this. This is one solution. You could use different protecting groups. If you did, you would have to use different reaction conditions than they did here in this example to remove those protecting groups. So here we need to, because we want to form the amide between the carboxylic acid of alanine and the amine of glycine, we need to protect the amine of alanine and the carboxylic acid of glycine in order to form that single dipeptide. And so in this example, the book has chosen to put a Bock group on the nitrogen. They used the conditions we showed you on Monday for doing that. And then they decided to make a benzyl ester for the carboxylic acid of glycine, and they used those Fischer esterification conditions. Once they completed those protecting group steps, the protecting steps, then we now form the amide using DCC. Okay, and then now it's time to remove the protecting groups, and because of the groups that they've chosen, we have the ability to remove one of the protecting groups or to remove both protecting groups simultaneously. When would you want to remove just one protecting group? Yes. Exactly. If you wanted to make a longer chain peptide, more than just the dipeptide, then you would only want to take off one of your two protecting groups, so you could then perform a subsequent amide bond forming reaction. So when would you want to remove both protecting groups? When you're done, when you've made your target peptide. And because you always want to do, you want to perform as few reactions as possible, it's best when you remove both protecting groups to choose protecting groups that can be cleaved using the same reaction conditions. And you see the reason why the book chose the Bock and the benzyl ester groups is that you have options. With Bock and benzyl ester, you can cleave either one and leave the other one intact. They've shown here hydrogen, palladium, carbon, cleaving the benzyl ester, leaving the Boc group intact. What would you use if you wanted to cleave the Boc group and not the benzyl ester? You could use either HCl or trifluoroacetic acid because you have to use HBr if you're cleaving the benzyl ester using acid. Here they used trifluoroacetic acid to remove the Boc group after they cleaved the benzyl ester, but you could do it before cleaving the benzyl ester and it would only take off the Boc group. But then here, if you really wanted to remove both protecting groups, you would do it in one step. You would just expose this peptide to HBr. The acetic acid is just being used as a solvent. It's commonly used as a solvent when we use HBr. Okay, question, Brady. Yes, yes, very much so. So, in fact, the functional groups of the side chains frequently need to be protected in peptide synthesis in order to prevent them from reacting. So there's a whole nother set of side chain protecting groups. But unfortunately, we don't have the time to teach you about side chain protecting groups in class. But definitely, the synthesis of a peptide is affected by the functional groups in the side chains and adds another set of protecting groups that are required. Okay. All right, so here we see a case where tripeptide as opposed to the dipeptide is our target. So in this case, we took the N-protected dipeptide. So if we cleave the benzyl ester using hydrogen and palladium carbon, we could couple on another glycine in this particular case. And then now we're done. We want this allyl-gly-gly tripeptide. And so we use the HBr to take off both of those protecting groups. Okay? Any questions about our peptide synthesis? Okay, so it's helpful to think of our protecting groups in pairs. We pair a carbamate protecting group with an ester protecting group if they are cleaved using the same reaction conditions. Okay? So the first carbamate protecting group we taught you was the Boc group. The Boc group is cleaved using HCl, trifluoroacetic acid, or HBr, and we have an ester that is cleaved under the same conditions, and that's the tert-butyl ester, right? And these are very similar in structure. They both have tert-butyl groups in them, okay? Then we taught you the FMOC carbamate. That's cleaved using base. It's cleaved typically using piperidine, a secondary amine base. But we can pair that up with our methyl ester. Our methyl ester is cleaved using stronger base, using hydroxide. But if you use hydroxide to cleave a methyl ester, that's also going to cleave the FMOC. The FMOC is cleaved with weaker bases, but it can also be cleaved with stronger bases too. So these are both, you could cleave these two protecting groups simultaneously using hydroxide and water. And then we have our CBZ group. And that is paired up with our benzyl ester because both of these protecting groups are cleaved using hydrogen and palladium carbon. So if you use these pairs in instances where you want to remove two protecting groups simultaneously, then that streamlines your synthesis. And then you use a carbamate and an ester from different pairs in cases where you want to cleave one protecting group and not the other. And sometimes you can cross pairs and cleave both groups. We've seen that with the benzyl ester being cleaved using HBr. So you can cleave the benzyl ester with the Boc. You could cleave the tert-butyl ester with the CBZ. You could cleave the benzyl ester and the FMOC if you were using base in both cases. So there's some ways to go across the pairs, but it's easiest to just keep them paired up when you want to cleave both protecting groups. Questions? So just as an example of how what we refer to as global deprotection, or cleaving all the protecting groups at the end of your synthesis simultaneously, can make your synthesis more efficient. Here's a step from our synthesis of vancomycin back when I was a graduate student. These reagents we haven't discussed in class. We won't go over the mechanism. These reagents actually allow you to cleave a methyl ester and a Boc group simultaneously. So we have more possibilities than just what we're teaching you in class. But this compound, so we used Boc on the N terminus, and we used a methyl ester on the C terminus. And we had some side chain protecting groups, as I mentioned. So vancomycin has these phenols, these OHs, these 4 OHs, and we had to have those protected during our synthesis. They were protected as methyl ethers. Okay, and this is like the nuclear missile of deprotecting. It deprotects anything in its path. And so we cleaved actually 6 protecting groups in one step. If we'd had to do that stepwise, that would have been 6 steps in our synthesis. 1 step over 6, everybody, a kindergartner knows math well enough to recognize that that's a much more efficient way to do things. So it's very important to choose your protecting groups wisely so that you can cleave them all simultaneously at the end of a synthesis. Any questions? Okay, so now we're ready to talk about another way, an alternative way of synthesizing peptides, known as solid phase peptide synthesis. In solid phase peptide synthesis, we attach our C-terminal amino acid to an insoluble polymer, and then we attach the other amino acids in a stepwise fashion, step by step to the chain, with deprotections involved, of course. And then we cleave the peptide from that resin at the end of the process. Solid phase peptide synthesis was developed by Professor Bruce Merrifield. He worked at Rockefeller University, which is a private university in New York City. And he developed this process in 1969, so many years ago. And it is such a widely used technique that he was awarded the 1984 Nobel Prize for his discovery and development of solid phase peptide synthesis. So the solid part of the solid phase peptide synthesis is a modified polystyrene polymer. Now we'll learn much more about polymers in our final chapter, chapter 31, including polystyrene. This would be polystyrene if we just had benzene rings here. But this derivative of polystyrene has these primary alkyl halides coming off of a selection of the benzene rings in the polystyrene. Okay, and we just abbreviate it like this. And these primary alkyl halides are the handles that allow us to attach our C-terminal amino acids to the polymer chain, to the polymer bead. These polymers are usually just these tiny little beads. So this shows us the beginning of the process of synthesizing peptide by solid phase peptide synthesis. So we have this polymer bead, and then we treat it with a solution of our C-terminal amino acid and some base. Now we use FMOC. We can use Boc or FMOC in this chemistry. CBZ doesn't work very well for reasons we won't get into. But FMOC is much, much, much more common. So we're just going to show you solid phase peptide synthesis with FMOC. Okay. So we don't want a strong base because that's going to cleave. If we use piperidine, our secondary amine, or hydroxide, that's going to take off the FMOC group, and we don't want that yet. So we're probably going to use something like bicarbonate, sodium bicarbonate. That's a strong enough base to deprotonate a carboxylic acid, but it's too weak to cleave the FMOC. Okay. So what happens is we make the carboxylate. That just reacts. That's a strong nucleophile. That's going to react with our primary alkyl halide in an SN2 reaction and form this carbon-oxygen bond, attaching our first amino acid to the polymer bead. Okay. So once we get our first amino acid attached, we then deprotect the amine. Since we're using FMOC, we add piperidine. And then a feature that I forgot to mention in the first step is the purification. The purification of our product is very much simplified in solid phase peptide synthesis because your product is attached to this polymer bead. Your byproducts and any unreacted reagents are in solution. So all you have to do is rinse the bead, and that rinses away your byproducts, rinses away any unreacted starting materials. So it's a very, very simple way of purifying your product. Okay, so after this SN2 reaction, we would rinse, and that would rinse away any unreacted amino acid and base. We rinse after the FMOC group is cleaved, so we rinse away the byproducts. We rinse away any excess pyridine. That gets us ready to attach our second amino acid. So we use an FMOC protected amino acid and DCC, forming our amide bond. And then we rinse when that's done. And then we just repeat steps 2 and 3, deprotect, couple, with rinsings after each of those deprotections and couplings. And we do that until we have the peptide, the desired peptide. This technique works well for peptides of up to about 30 to 35 amino acids in length. Above that, we start to have some problems that I won't really get into. And so then once we have reached the desired length, after we cleave the FMOC group, now we have to cleave the peptide from that polymer resin in order to be able to isolate the peptide. And there are other resins than the one we're showing you here. But for this particular resin, this modified polystyrene resin, we would have to use HF, not our favorite reagent. Fluoride will, HF can eat glass. It can also eat your bones. So you want to be very careful anytime you're using HF. But we do need it in this case to cleave the peptide from that polymer. And then we purify the peptide. Okay? Any questions about this process? Yes? Yes. So you can buy the common 20 amino acids with the FMOC group already on there because it is because this process is very commonly used. So yes, you do need the FMOC group already on each amino acid when you couple it. Otherwise, you'll see self-coupling in solution of those amino acids. If it's FMOC protected, yes. The DCC does that job. If you remember the mechanism of the DCC, there's a nitrogen in DCC that's going to deprotonate the carboxylate group. For the coupling you're talking about? You're talking about this step here? Yeah, this one you do, and bicarbonate is a common one because you don't want it to be a base that's going to cleave your FMOC group. Okay, good questions. Other questions? All right, so the advantages of this technique are that the purification is streamlined. The purification of each intermediate simply involves rinsing that polymer. Okay, so it's very, very straightforward. And it's an iterative process. You're doing the same things over and over again. So because of the simple purification and the iterative nature of the process, it actually can be automated. There are automated peptide synthesizers, these instruments that have bottles for, you just make up solutions of the FMOC protected amino acids, solutions of the piperidine, solutions of the DCC. There's other reagents similar to DCC that we use sometimes. And you just program the synthesizer to tell it which time to use which bottle, and it will synthesize the peptide for you. Okay? We actually just bought one of these. It just arrived yesterday, in fact. There's 3 groups three of us organic chemists who are involved in peptide synthesis, myself, Dr. Price, and Dr. Michaelis, and we're sharing this peptide synthesizer that just arrived yesterday. So we're really excited to use it. Our students, of course, are really excited because it's going to simplify their synthesis of peptides. So you might wonder, why would you not want to use solid phase peptide synthesis? Why would you want to make peptides in solution, kind of the traditional way, instead of this solid phase method? Well, there are some drawbacks to solid phase peptide synthesis, and it is important to understand these drawbacks. There's two main drawbacks. The first one is that excess amino acids and reagents are required for each step. And that's because your reactions are all heterogeneous reactions, meaning they have two phases instead of homogeneous reactions. Your peptide is not in solution. It is on this insoluble polymer. And so your reagents are in solution. They're reacting with a peptide that is not in solution. So when you have biphasic or heterogeneous reactions, they tend to be much slower. And in order to speed them up, we use excess. We increase the concentration of the components that are in solution. So you're typically using 5 equivalents of each amino acid just to attach one to a peptide. So that's not terribly efficient. With our 20 common amino acids, it's not a big deal because they're relatively cheap. But if you were coupling on unusual amino acids, ones that you had to put a lot of effort into synthesizing, you would hate to throw 80% of your amino acids away in that rinsing step. Okay, so that's a drawback that comes into play sometimes. Okay, and then the second drawback is derived from incomplete reactions. So none of our peptide coupling or amide bond forming reactions will go to 100% completion. We can typically get them to go to maybe 95, 96% completion. But when we're making a long peptide chain, those incomplete reactions cause us a problem. And I'll show you what we mean by that. So here's our polymer. Here's our first amino acid A. We're going to perform our first amide bond forming reaction. And we're going to attach amino acid B. Okay? But this reaction doesn't go to completion. We're going to have maybe 95% of this, and then we're going to have about 5% of this. So what happens when we add amino acid C? It reacts with both of these. Okay? So we get our tripeptide, but then we also get this dipeptide, okay? And we're going to have a little bit of this dipeptide left over, okay? So we've done 2 couplings, and we now have 3 things, 3 different peptides on our resin. Most of it is this, but we have a little bit of each of these dipeptides. We add a 4th amino acid, and we introduce a 4th byproduct, okay? So incomplete reactions give us a new byproduct each time we perform a coupling. And so the individual purifications of intermediates are simple. We just rinse the resin. But at the end, when we take the peptide off the resin, we're not taking just one peptide off the resin. We're taking all of these peptides off the resin. And so once we cleave them all off the resin, we have, if we're making a 30 amino acid peptide, we have one major product, but we've got 30 minor products that we now have to purify. And that becomes challenging, okay? In fact, when Merrifield demonstrated the utility of his solid phase peptide synthesis method, he constructed a protein called ribonuclease. Ribonuclease has 128 amino acids. It was a remarkable achievement in 1969. Nobody thought you could synthesize a protein back then. It took him 6 weeks to synthesize. Okay? That's not bad. 6 weeks to perform over 250 reactions in this automated fashion. That's pretty impressive. But The drawback was that it took him 4 months to purify the protein. Okay? Nowadays, it wouldn't take that long. There have been advances in purification methods, but it still will take longer to purify your final peptide or protein than it will to synthesize it. Okay, so those are some of the drawbacks. That's why, while solid phase peptide synthesis is used frequently, it is not used exclusively. There are some peptides for which solution phase synthesis is going to be more efficient. Questions? All right, let's talk about protein structure now, okay? And there are different levels of protein structure. We'll start out with what is known as primary structure. So the primary structure of a protein, refers to the sequence of amino acids. Okay, so whenever we're talking about primary structure of a protein, all we're looking at is the sequence of amino acids that we have. And we know that the amides are planar. We also know that we can rotate about the carbon-carbon and carbon-nitrogen bonds involving the alpha carbon, so there's a twist between our amide bonds. And because of that twisting, because we have different conformations, we end up with what is known as secondary structure. Okay? Secondary structure refers to the 3D conformation of regions of a protein. Okay? So in addition to being controlled by this rotation about these carbon-carbon and carbon-nitrogen bonds, hydrogen bonding between amides in the backbone plays a major role in determining the secondary structure of proteins. Okay? So we have our amides, right? They look like this. And we can have the NH of one amide hydrogen bonding to the carbonyl of another amide. Okay? And so that allows us to cause these peptides to fold into various three-dimensional conformations. There are two secondary structures. There's lots of secondary structures, but there are two that are much more common than the rest, and those are the ones we're going to focus on. The first one is the alpha helix. Okay? So an alpha helix is a right-handed helix, or a helix that has a clockwise twist as it goes up. And you can see here in this diagram, we have the carbonyls. The oxygen is kind of coming off the top of this chain as it curls up. The NH is coming off the bottom. And so we have the ability to form these hydrogen bonds. Between residues, they would be known as I and I plus 3. So residues number 1 and number 4 in the chain. Number 2 and number 5, they're able to bond to each other. Residues is just a term we use for amino acids when they are present in peptides or proteins. So you see that the hydrogen bonds that are holding this helix together are roughly parallel to the axis of the helix. Not exactly, but pretty close to being parallel to the axis. One full turn of the helix is basically 3.5 residues. So that means that when you go 2 turns, you've essentially had 7 amino acids that would span those 2 turns of the helix. So the side chains are represented here by these orange balls with R in them. This particular figure from another textbook shows it better, in my opinion. Here we're looking down. If we look at B, we're looking down the axis inside this alpha helix. This one is made up only of alanines. These are just methyl groups. And you see that the side chains just poke out sideways from your alpha helix. So if you had amino acids with longer side chains than alanine, than the methyl group of alanine, you'd have longer side chains coming off of that helix, okay? So you can accommodate many, if not most, amino acids in alpha helices, although some prefer the alpha helical conformation more than others. But there's one amino acid you won't see in an alpha helix, and that is proline. Proline has a secondary amine because the amine is part of the side chain due to the ring that forms. And when it makes an amide, it no longer has an NH that can form a hydrogen bond. So you will not see proline in an alpha helix because it cannot generate a hydrogen bond. All right, so our second type of secondary structure that we'll focus on is the beta sheet. Your book calls it a beta pleated sheet, but most people I know just simply call it a beta sheet. So a beta sheet is going to look like this. So instead of having this coil, we're going to have these sheet-like strands of our protein, and we're going to have hydrogen bonds going across the strands from one strand to the neighboring strand. Okay, so you see all these hydrogen bonds linking these strands together, making a beta sheet. The side chains are represented by these orange balls. I wish they'd chosen another color that wasn't close to red, but anyway, you can see that they alternate poking up or down, up, down, up, down. So the side chains in a beta sheet are going to alternate between coming off the top and the bottom. Most of those side chains will be very small. Beta sheets are rich in glycine and alanine. If you can have a handful of larger amino acids, ones with larger side chains in beta sheets, but not too many. If the side chains are too bulky, then it's hard to bring those strands close enough together to engage in hydrogen bonding. Okay, so we need a lot of alanine and glycine to form beta sheets. There are two types of beta sheets, parallel and anti-parallel. And this has to do with the direction of the strand in terms of the amino acids going from N to C or C to N. Anti-parallel beta sheets are most common. You see the way this is drawn as you go from left to right, NC, NC, NC. That's the direction we're going down the peptide chain. On the other strand, CN, CN, CN. We're going the opposite way down the chain, as represented by the directions of these arrows. One thing I need to mention is that the strands of a beta sheet are usually part of one long peptide chain or protein chain. So in between the strands, we usually have a loop, okay? And it's much easier to have a loop connecting anti-parallel beta sheets, because if you have a loop, you're turning the direction from N to C to N. The parallel beta sheet, you have to have some kind of a funky loop in order to connect two strands going in the same direction. So this is more common than that. And the hydrogen bonds line up better in the anti-parallel sense. So an anti-parallel beta sheet is stronger. So sometimes we represent alpha helices and beta sheets by these ribbon diagrams. And here is a peptide, or a protein, spider silk. Spiders use silk to make their webs, and the webs have to be elastic. When a bug hits it, it has to stretch a little bit, but it has to be tough, has to be strong. It can't break. So the alpha helices impart elasticity because alpha helices can stretch. When a force is applied to an alpha helix, it can stretch. When that force is released, it goes back to the helical conformation. The sheets cannot stretch, but they impart strength and toughness. So if you have the right ratio of alpha helices to beta sheets, you get a material such as spider silk that is ideal for making spider webs. And we see in this ribbon diagram, the helices are represented by these green regions. We see that the beta sheets are represented by these purple strands. We have arrows showing the directions. So you see this is an anti-parallel beta sheet. And we have these yellow loops that are showing the connections between the strands. Okay? Any questions on how we're representing our spider silk? All right, our next type of structure is tertiary structure. Tertiary structure is the 3D structure, 3D conformation of a protein or one chain of a protein, okay? And that the tertiary structure certainly is affected by secondary structure, but there are other elements that play a role as well. One of these we saw on Monday when we were talking about oxytocin, and that is disulfide bonds, okay? We can form disulfide bonds between two thiols from cysteine amino acids. We can do so between cysteines on the same chain, that makes a ring, or we can link cysteines on adjacent chains, joining two peptide chains or protein chains together, and that creates what's referred to as quaternary structure. When we link two different protein chains together, we have quaternary structure. Insulin has both types of disulfides. Insulin has two chains, the A chain and the B chain, so it has quaternary structure. We have two disulfides that link the A and the B chains covalently, and we have a disulfide between two cysteines on the A chain that forms a ring. Okay, so quaternary structure affected by disulfides, also by local secondary structure. And this figure here shows us very nicely all the different types of non-covalent forces that can contribute to tertiary and quaternary structure. We also have covalent bonds such as disulfides. We have hydrogen bonds. Those can help us make beta sheets and helices. We also have other attractive interactions between the side chains of our amino acids. We can have van der Waals interactions between nonpolar side chains. We can have electrostatic attraction, also known as salt bridges, between charged side chains. So you can see we have lots of different types of attractive forces that can cause a protein to fold into a certain three-dimensional shape. So we'll stop there. We have a couple of other things to go with proteins on Friday before we jump into carbohydrates in chapter 28 on Friday.